Okay. So, welcome to the Tuesday lecture on CMOS MEMS. I brought you a book again today. This is about this tactile sensor that we discussed yesterday in one of the exercises, and also that I presented briefly during the lecture of the week before. And maybe you can look up on page 19. I mean, many pages are interesting, but on page 19 you have a 3D view, a detailed view, a schematic view of that structure and how it deforms when it is loaded with forces. And then I think on page 41, yeah, you also see a partial view of the structure when it is being deformed, so that you can also form a 3D image of how this deforms. And yeah, it's a PhD thesis by Matthias Hermann, who is now an engineer in an interesting position at Infineon in Munich, and does a lot of numerical simulations and yeah, interesting sensor work. I'm not allowed to talk about that. I'm not able to talk about that anyway. And so this was his work, and he analyzed this structure in real depth mechanically and piezoresistively, and with simulations and new designs, some of which were also patented. And I mean, the sensor has been put to work in a big machine of size, as I mentioned, in order to be able to measure 3D coordinates. So, well, you're in the front first, and please hand it over to your colleagues. So with this, I would like to continue with some examples of micromachining, MEMS micromachining that are out there and have been, I mean, you know, making a big splash in the community. And so let me first categorize these CMOS micromachining methods. There's always many mental pictures of subdividing the jungle of ideas. Yeah, and so here is one. This is according to when the micromachining occurs. It can occur before the CMOS process. So imagine a wafer on which one does some micromachining and then covers it all up, and then the wafer looks like a wafer, pristine wafer. And the machines don't know that there is something buried below the surface. The archaeology will have to tell what is below the surface and put it to work. Yeah, and so then the CMOS process can proceed. That's quite ideal. Yeah, yeah, because well, you don't have to carry about thermal budget. Yeah, because the thermal budget invested for the micromachining has been invested before the CMOS starts. Then one can also consider intra-CMOS micromachining, which means in between. Intra means within. Within the CMOS process, you can imagine a process that starts with the first steps of the CMOS process, and the CMOS part is stopped. Some other things are done, digging into the silicon, depositing layers, removing them on the CMOS part, and then covering all up, and then continuing with the CMOS part. But maybe possible. So that's intra-CMOS. And then post-CMOS is that actually the process when everything occurs after the CMOS process. So the wafers come out of the fab. They have been designed by the engineer in order to receive some additional structures at appropriate locations, or to be micromachined at appropriate locations to turn these microelectronic structures into sensor or actuator structures. Well, that's pretty good when you would like to avoid discussions with the CMOS foundries. You submit them a design, they don't know what the heck is this about. Can't be real, because it is not a microelectronic structure necessarily in some parts. But there is no change of their technology, so they don't have to worry about stability of technology, and then they produce it at your own risk. And your own risk is your own chance. You make it into a sensor by adding your micromachining steps, MEMS last. And of course, it is clear that we can do surface micromachining and bulk micromachining, as we have seen. in these various ways. So you could now invent, you know, when people start to do categorizing, then of course you have this multidimensional category Cartesian arrangement. You could do, can we do surface micromachining in the intra-CMOS or in the pre-CMOS or in the post-CMOS? Can we do bulk micromachining? And if there are other dimensions, other categories, then you might think of other opportunities to do something creative, filling out gaps in some bigger schematic scope. Yeah, so here are some names of groups, universities, companies who have been active in promoting, in the early days, some of those micromachining structures. Sandia, I have already mentioned that earlier. UC Berkeley was instrumental in developing these micromotor surface micromachining structures. Analog Devices has been among the first companies to propose inertial sensors based on vibrating thin film structures on top of CMOS or within CMOS, intra-CMOS. So all kinds of things. And bulk micromachining, Bosch is well known for their pressure sensors, for their gas flow sensors. MIT, UMichigan, Tohoku University, they also did pressure sensors in those early days. Tohoku University, accelerometers. ETH Zurich did many sensors, and one vertical Hall sensor was a micromachine sensor. Now we know how to do vertical Hall sensors without micromachining, thanks to cooperations with Micronas. So here are now come some examples, some of which I will explain in more detail, others in less detail, but you can imagine a little bit this as a challenge, that has been solved by engineers. So clearly, what does that look like? So on the left you have some circuitry. So this looks like a CMOS part with some P-tub. Tub is also a name for well, P-well, N-well. So that's clearly complementary MOS technology. And then some of those materials extend over this micromachining area. And this micromachining area is recessed or receded below the surface of the CMOS wafer surface. The CMOS wafer is here. So it is that was produced by producing some MEMS infrastructure before the CMOS process by diving into the silicon, obviously with a KOH etching, with this inclined wall. That's typically KOH, with a flat bottom, a few micrometers, and then deposition of layers of conductive materials, some polysilicon, some nitride insulation layer, some more polysilicon filled with oxide and more up to this level. And then there was certainly a planarization step also to make this whole thing planar. And then you can do CMOS on top of that flat wafer, some of which is not exposed silicon, but something else, and it is protected by a layer so that it does not oxidize. This nitride layer that was there to really cover everything up and make it insensitive to whatever process occurs there. So this needs to survive high temperatures, definitely. But polysilicon can, and oxide can also survive high temperatures, so no problem. And then what is the structure? A micromechanical device. So you see a segment of a beam, which is representative of some inertial structure. Inertial sensors very often work with fingers, and other fingers that protrude between those first fingers, so-called interdigitated structures. Digitus means the finger in Latin. And so interdigitated means interfingered structures. And then one of those set of structures can move while the other is fixed. So you see one fixed, and then from the other side, out of the window, there might be something coming from the right, and it is also fixed at some point, but it is fixed in a way that makes it somehow elastic enough to now move between those horizontal fields. So that is, and then what are those interdigitated fingers doing? Yeah, they can be charged to different voltages. We can measure a capacitance between one and the other set, and if the distance changes, of course, yeah, because capacity is some epsilon times area divided by distance. That horizontal distance, if that changes, the capacity will change. There, that will be indicative of maybe some acceleration imposed on that chip that lets one of the fingers be closer to the as very often inertial sensors work, and we will see some examples of these interdigitated fingers here. Yeah, so you see now kind of a top view or oblique view of this micro machined part, where you see some set of fingers that extends here very rigidly. Probably it is fixed on the side here, and then we have some. It's not even sure. No, it's not sure. Likely the fixed fingers are those here. There are actually two sets of fixed fingers. So that's a bit delicate. We will see that in the later chapter about inertial sensors in chapter 6. And then this front part is part of a larger structure, that is suspended on springs and that can move to left and right. And you see that one distance is larger than the other distance, so there is an asymmetry in capacitance, and that differential capacity can now be used to measure the shift of that central structure, for instance, under an inertial force. Here are some examples. Here is a finger that is ending here. Here's another one that is ending, as you see. So there's many ways to design these structures. And you see that indeed this started with KOH etching, and then elaborating some silicon and so on, oxide structures, and at the end this is sealed by a nitride cap, and then comes the CMOS process. There is another variant proposed by Analog Devices. Analog Devices still produces inertial sensors. Now they have 30 years of experience in this area, so they most certainly are profitable. And definitely one of my postdocs works there, Zeno Valchev, and so they do many things apart from accelerometers and gyros, but that is an important part. And so what you see here is another way. It's also pre-CMOS. So you start with a silicon substrate, and then you do thin film deposition, some oxide, some polysilicon base metallizations, and then another oxide, and then some thick layer of mechanical silicon that will then again be shaped by etching into these vertical structures, into these finger structures. And you see that this is done on the entire wafer. But then at some point, part of that is cut, is etched away again, not cut. It is etched away, removed down to the silicon, including this little protective layer, the green layer that is here. Everything, the blue silicon is exposed, and then this whole structure, which has partially these potential micromechanical structures here on the right, in certain areas, and other areas are exposed. That is put into a furnace to create what is called epi. Now epi is short for epitaxial silicon. Now epitaxial silicon is also silicon. It's also monocrystalline silicon, but it is grown in a process that promotes this monocrystalline shape. So silicon is deposited from some silicon-rich gas, silane, dichlorosilane, tetrachlorosilane, whatever the process is, at pretty high temperature. And then the silicon condenses, adheres, absorbs on the surface, migrates to positions where it feels comfortable, that is in crystalline positions, with tetragonal binding. And then the silicon grows layer by layer to the thickness of what was added at the beginning in micromechanical structures. So epitaxial silicon is let's say 1,200 degrees centigrade, 1,100 degrees centigrade. There's different temperatures, but it's high temperatures to have high growth rates. And there are other companies who use epi. So if you go to Bosch, they will talk about the epi-poly. Epi-poly. Now, what is epi? Epi means single crystalline, and then the poly means polycrystalline. Now what? So with epi-poly, Bosch means a silicon layer produced by that in those reactors at high temperature with high growth rate to make 10 micron thick layers if needed, but on a substrate that is not monocrystalline. If you do the same process on a silicon oxide, the atoms who migrate there don't know what is the crystalline orientation. So they will nucleate in many patches of seemingly monocrystalline areas or aggregates, but there were many of those at many positions. And then those grow, and there is a boundary between each of those pairs of regions, and that is a grain boundary, and that is what makes polycrystalline material. Volumes that are monocrystalline separated by grain boundaries because of their different orientations. So it looks like here, there was this, oh, there's my pen. Here, so there was a sensor oxide grown, and then nitride, and then poly, a blanket poly here, and then some additional spacer oxide, and then more silicon, and then the epi growth, and then more planarization, and then the whole thing is basically ready to receive some CMOS. And then once the CMOS is done, you can remove the blue area if you want, the light blue area. And that releases a structure to produce something which looks like that, released silicon, mechanically mobile silicon. So this is shown here, where actually, the circuit area has been defined, and some interconnection lines of the circuit are now also protruding over the micromachining, and then electrical signals can go via this base polysilicon layer into those released mobile, locally supported structures that can then move, either be stiff or move various ways needed for an accelerometer or a gyro. Okay, here is another structure. So what is also handy is SOI. So what is soy? Some people say soy, others say SOI. It's not French. It doesn't mean yourself, soi. It's a silicon on insulator. Silicon on insulator. And so silicon on insulator means that a wafer has been prepared that has the following structure. So there's a wafer, there is an insulating layer, and there is another monocrystalline silicon layer on top. So this is silicon oxide, and this is silicon, and here also we have monocrystalline silicon. And how does one produce this monocrystalline silicon on the silicon oxide? It's an interesting question. You cannot grow it, because how would it know what the crystallinity should be? You would produce polycrystalline, as I just said. So people do wafer bonding. They take a silicon wafer, make a silicon oxide on top, and then bond in a so-called Nordic bonding process, a second wafer, which chemically adheres to that oxide, like the bottom layer adheres to the oxide. So two wafers, and then you can thin the top wafer, remove the top wafer to a remaining thickness of 2 micron, 1 micron. Then you need to be precise in your polishing. Or you do an implantation of oxygen deep into, or and then so high energy oxygen implantation, which then is annealed at high temperature. So the oxygen condenses with silicon to an oxide layer and retreats from the surrounding silicon. So you have the original silicon on both sides and oxide layer between. Or you do bonding, where the second wafer has been prepared with some hydrogen implantation. How can people have these ideas? So implant hydrogen to a depth of micron, 2 micron. And then you do a bonding. And then there is a tracking process, because the part where the hydrogen is kind of weakened. So if you know how to do it, you shear off, you remove that thick top part of the silicon, and you have only this thin part. So you can bond it to the substrate below left. And that wafer can then again be implanted with hydrogen, and again be bonded with multiple transfer on different silicon oxide covered wafers to have many such SOI wafers. And such an SOI wafer, of course, to a CMOS process looks like a pristine wafer, because you can do your that's the wrong pen. I let it hang, not to be tempted anymore. And here you can do your circuitry. So no problem. But you can also do other things. So you can, instead of having circuitry, like here, here you see circuitry, you can also get access to that material, remove it, for instance, and then reach the silicon oxide below. And then this oxide below can be removed by HF etching. Yes? For this tracking process, yes. Why hydrogen? Well, ask the technologists. I don't know why hydrogen is particularly good. Seems to work, but I know no fundamental reason why hydrogen works better than something else. The smallest molecule maybe is able to penetrate most easily and then goes deep. I don't know. Could be, but don't blame me if I'm wrong. So you can remove that layer of dielectrics here, and then you can etch into the silicon using, for instance, deep reactive ion etching, with vertical etch walls, as we've seen. And then you can you expose the silicon, the buried silicon oxide, which can be removed using hydrofluoric acid or some fluorine-based vapor phase etchant to remove it, and then the silicon is released. And do you think that these structures who are released now will just fly away, or what do you think? What is with these structures? I'm asking because some people have different abilities to see things in 3D. So that's why I'm asking. Well, why don't those fly away? In the third dimension, they're attached, of course. They don't need to be under etched everywhere. They can be under etched until somewhere. And indeed, that's possible. The oxide edge stops somewhere. Like this structure. Oh, this structure is also not under etched completely. So this structure stands still on the silicon, and this structure can also stand still on the silicon in the back or the front. Of course. Thank you. And then you might also think that on Well, one can even use multiple such layers. So imagine here a spacer layer. It could be silicon, or it could be something else, some other oxide. Then at the end of this more complicated sandwich, we attach again by anodic bonding a thin silicon. Then you can release and produce cavities and diffuse by whatever. So this is it says mirror metal. So this is a structure that is elevated somewhat above the substrate, unlike the top structure, in order for it to be able to rotate to an appreciable angle. You see electrodes down here, electrodes that are contacted vertically to some other metallization structures, I presume, and they like here. So you see here an electrical contact to this electrode, and of course this floating mirror is attached somewhere with a thin structure that allows it to rotate. And then if you apply a voltage between the two, there will be an electrostatic attraction force, and the mirror will be tilted in one direction. And if you do it with a voltage on the other side, then it will be tilted in the other way. And so you can have a mirror that can take any position or as desired. So there have been many mirrors fabricated using micromachining, and of course the nice thing is that they're fast. And the best example of a micro mirror is that of Texas Instruments, which you will see. It's a fantastic device. It is not done in a pre-CMOS, it's done in a post-CMOS process, which gives it much more flexibility. Okay, then I have here the silicon porosification. That's also interesting as a pre-CMOS process. I'll switch one page and then come back to the previous one, because this is the starting. Simon Armbruster was a PhD student entrusted to me as a doctoral father by Bosch. I always say I was the academic Feigenblatt, the fig leaf, that was needed for the pewter, of the company, because they wanted to make him a doctor and they needed a university. But he was a really good student. He did the following. So when you etch silicon, you may have the impression that one just removes the material. But if you do it electrochemically, electrochemical etching is a highly elaborate art. You may have heard about the topic of anodization of aluminum. How does one give aluminum different colors? One etches pores, nanoscopic pores, and fills those pores with color. And then an aluminum becomes space gray or blue, yes, or any other. Oh, that's painted. That's not anodization. But that's a method that is very common to porosification of materials by electrochemical etching. So the etching does not proceed in kind of a wave on a large front, but because of the electrochemistry, it is kind of self-concentrating and proceeds on the tip of what is already etched. So you get little channels etched into the material, and this is done regularly on metals. And it depends on the voltages and the concentrations and the temperature and many parameters. If you would like to close here to hear better, don't hesitate. We can just open on this side. Yeah. Don't. We can. This side is okay. This. Yeah, exactly. I can also open better. And so this can also be done with silicon. Porous silicon is well known. It is done in a hydrofluoric etchant with a counter electrode, silicon beam electrode put to a potential, and then a reference electrode also in this 3 electrode setup. And then by applying appropriate voltages, the silicon is not etched as a planar surface, but it is porosified. And that also depends on the doping of the silicon. So in this case, what you see here is a starting structure crappy picture from the original publication, which says N. Does it say N? I thought it was P plus. Yeah, this should be P plus, and then there is P silicon below. Yeah? So let's make this P plus, and this is P. And then here we have some N structure, N silicon, which is also covered by silicon nitride. So by exposing that wafer to hydrofluoric acid under a given etch condition, what will happen is that there will be a fine-grained porosification at the surface, and then a rougher porosification in the P region because of this dopant dependence. So you see the result here on the side. And then, of course, one takes out the wafer, one cleans it, one dries it, and then one puts it into an epitaxial reactor, this epi reactor. So silicon is raining down on this surface that is not, there is still a rough surface. I mean, there's silicon with many pores. So there's a lot of silicon. Silicon deposits on that silicon, finally closes everything. So the surface is becoming closed, and then more epitaxial silicon grows to a thickness of 51 B, a few micrometers. And so there is this rough porous material buried below silicon, but at the high temperature at which you do that, the silicon in the cavity is so hot that the atoms on the surface migrate also, and they migrate to places where they are, most favorably bonded. And so you can imagine this like a material with a surface tension that tries to make the area as small as possible to flatten it out. Water does not by itself become very, highly corrugated. It flattens itself to become flat. Of course, also under the action of gravity. It's also an effect. But the surface tension is an important effect, and so the surface tension makes this cavity hollow. Silicon is either migrating to the bottom or to the top, and then we have a cavity that is totally enclosed. And so at the end, you have an epitaxial silicon, and that silicon is monocrystalline, because making pores into silicon does not disturb the crystalline order of silicon. There is still the crystalline order of the silicon, and whatever grows on top takes over this order and combines into a dense layer, which is monocrystalline. It's a wonderful idea. Yes? Yeah. So what is in there? We would like to have a vacuum. But it's not a vacuum. It's oxygen will react with the silicon. So there may be a little oxygen layer. But there may still be hydrogen enclosed, for instance. And that causes a little bit of a problem. There are some methods to getter gases from cavities, but not in this circumstance. Okay, so we have this little residual pressure of something which have to be taken care of. And now you can imagine this structure. Let me draw this original wafer. And let me draw a cavity, and then this. Okay, here is some N, and then we have epitaxial silicon grown on top. So now we should have a flat layer if I was able to draw that flat, and now on this wafer you can do circuitry. For instance, you can integrate some piezoresistor. Piezoresistor. You can do, of course, circuitry here. This structure under a pressure will deflect, and so this piezoresistor acts as a deformation sensor, piezoresistive deformation sensor, as we will see in chapter 4. So you can have a pressure sensor, P, and let's call this P0, yeah, residual pressure. The difference of the pressure will cause a response of the combination of these piezoresistors if they're combined appropriately, arranged appropriately on the surface of this membrane. And the membrane is not just a bridge, it's a real membrane with a cavity that may have a square or a round shape underneath, totally surrounded by silicon, and a real enclosed cavity. So you can have any sensor geometry over a cavity by appropriately designing this N region definition that will where the porosification will stop, not proceed. So it's a well-defined geometrical definition of the structure. So this is the basis of pressure sensors by Bosch, yeah, and of course Bosch makes a lot of money with that idea. Simon Armbruster worked his way up quite steeply in the hierarchy. He's now one of the top managers after having been sent to East Europe to build up the business there and fabs and so on. Yeah, powerful guy. Yeah, and so this idea was taken up by others. Here you see the name of N. Zimmermann, IMS CHIP, which is a research institute, having at its disposal also a lot of CMOS and technologies. And so they have proposed the following, a so-called, now I have to say it, a pick, crack, and place process. Yeah? So you can imagine this thin layer of silicon now, this epi layer, a few micrometer thick, to be suspended on some silicon pillar and otherwise separated from the substrate below by this porosified or porosity-based cavity. Roof layer. And this roof layer can now receive microelectronic chips or microelectronic structures, circuitry. Yeah? And then one can do a deep reactive ion etching of such a microelectronic circuit all around, almost all around. I mean, the chip should remain suspended, maybe at the edges, suspended by some remaining silicon structures. Let me see if we can see that here in magnification. Yeah. We can imagine that the chip is still suspended here, and at all four edges, whereas the etching etched down here and also on the third and fourth side vertically through this thin silicon layer. So we have a thin chip membrane suspended by four struts, and then in the next process, that chip can be picked up with some vacuum tool, removed by crack. It can be picked, can be cracked, and it can be placed somewhere. And the advantage is that the chip can be very thin, 2 micrometer thin, or so flexible if it is long enough, integrated into some flexible electronics. That's a very neat example of the use of this porosification technique. Part, of course, from the evident commercial success of Bosch's pressure sensors. So then let's look at some intra-CMOS micromachining. So again, there is surface micromachining and bulk micromachining. So you see again names of companies, Analog Devices again, Infineon, Freescale, formerly known as Motorola, Fraunhofer, EMS, University of Duisburg, etc. Yeah, so many people have done that, and bulk micromachining likewise. And I'll show some examples of these technologies. So here are some slides from Infineon, which were quite stimulating, I remember. presented at the Transducers conference in 2001 in Munich. Yeah. Nobody knew what Infineon was doing. Yeah, in MEMS technology, really, and then there was this conference, and they submitted tons of abstracts. They said, okay, probably the management said, yes, you can present as long as you don't cost travel costs. So they finally they submitted, because the management of companies is always, looking at the finances. I had a big fight with the CEO of Bosch because of Simon Armbruster, who had another abstract prepared and accepted at a conference. And then the manager said, you're not allowed to go for financial reasons or whatever. But I sent a letter to him saying that this was an intention, the best intention of the candidate to present his results to the scientific community, etc. What will a professor say? It's important to get the friction. And then I'm persona non grata. One does not speak with the CEO. There is layers between the common people and the Pope. I'm laughing about that. It did not disturb my career. I found it interesting to see how companies are organized. And so anyway, Infineon, another highly stratified company, presented many interesting results at that conference. And here is an example of intra-CMOS. So you can imagine that the CMOS was performed until about this layer here. So that's what came before. And then there was, that's up to polysilicon. So polysilicon is 650 degrees or so. So if you have a deposition process for the thick polysilicon on the right, that does not exceed the temperature or remains even below, then you're safe. So that's what they did. So they have some, they did some preparation actually with this low-cost oxide already in, so there's also a little bit of in here. But then there comes this intermediate part with elaboration of a first polysilicon layer, the electrical contact layer, which is actually maybe one of the CMOS polysilicon layers, then an isolation layer, oxide, then a thick polysilicon layer, which is structured, for instance, removed on the left. Then there is more oxide deposited, filling those gaps and covering up everything. There is another polysilicon, the roof polysilicon, which is then covering the whole micromachine structure with some holes etched into it, so that the white part, which was oxide, can be removed in a sacrificial process by HF, vapor etching, for instance. And then you have this micromachine structure in here, which is covered by a polysilicon with holes. And then you do another deposition, for instance, this thick dielectric layer on top of everything, plus some metallization and a passivation layer. And then the micromachine structure is totally encapsulated. Very handy. And you have done the job of encapsulation as well. It's always a challenge with micromachine structures. How do you handle them? Or let no dust go on them, because if you encapsulate the dust with it, then they won't work, and you have done all the work without a result. So this does the job, and thereby the CMOS process, or BiCMOS, bipolar CMOS process, is finished at the same time. So quite an interesting approach. And again, these structures are integrated structure that can do all kinds of things. So you can see these pairs and this mobile structure. So pairs of electrodes for making differential measurements with respect to the mobile silicon, which is represented by those parts. The others are fixed. So these both of them are fixed And then you see also some stopper structures that prevent the mobile structure from bumping into the electrodes, causing short circuit. These are all design ideas. And you see this coverage, the hermetic roof, the polysilicon, the oxide, and the passivation are all there. So that's very nice. Yeah. There's another idea also by Infineon from there. Yeah. So what has happened here? It's a standard CMOS process. Then there comes a micro machining module where again some thin sacrificial. So this is sacrificial etching here also of the oxide. The thick field oxide is performed through some openings that are not shown here because they're closed. But you have to think that there are some openings that are to remove the oxide in the middle, and then you have, for instance, here some polysilicon structure, of course, with holes that need to be closed, and then some stiff structures made of the remaining dielectric layers, for instance, that make this a stiff membrane that can, however, move up and down by the flexibility of the size. So this is a pressure sensor, and we can look at some structures here. Again, sacrificial etching and SEM pictures, scanning electron microscopy pictures, micrographs with this removed oxide, and then here a slightly thicker polysilicon. You see also here the area where actually the oxide was etched away from below. There were certainly on the front also such openings that allow to reach that oxide. And then during the growth of the other dielectric layers up to the passivation, those holes were sealed again, and the cavity etched previously is therefore sealed. And membranes, 30 membranes, are pressure sensors. So they demonstrated pressure sensors for rather high pressures. So at the time I didn't appreciate so much, but in the meantime we have worked on some 600 bar pressure sensors, and it's a real challenge. Also experimentally how do you apply such pressure. You're not careful, the apparatus just fly around the ear. Safety precautions to be taken. And they have many such elements, a whole array. So they can have a lot of capacity, and the capacity in the top polysilicon with some subjacent electrode allows to determine the level of the pressure. Yes. Yeah. The CMOS part on the here we don't see it. It must lie here to the right hand side. So CMOS must be about here. Yeah. So that here we can't see it. It's just a fragment of the micro machine part, and of course the CMOS is here on this side. Yeah. Even before? Yeah. Which one? Here we don't see the circuitry either. Yes, this is just the micro machined part that we see here. So you can imagine these beams to end somewhere, and then behind, there is, or to the left and right, is the circuit. Yeah, sure. Thank you for your questions. Okay. Yeah, here is another variant also by Analog Devices. They call it the IMEMS process, and so they again have some CMOS part. Yeah, so there's the BiCMOS process is interrupted after the field effect transistor polysilicon gate fabrication, yeah, and the bipolar transistor, emitter, collector, and plus diffusions. So some of the structures are done, and then there's an LPCVD nitride covering everything for protection. Yeah, one of those layers is this this nitride, and then on top of that, this MEMS poly is grown. Yeah. And then finally, the remaining process steps of the CMOS and bipolar process is done. And then this can be under etched again. That's the MEMS release thing. Well, here's another idea by Infineon. It's also interesting process. So here they do bulk micromachining. So you see these cavities, little cavities with some holes even, yeah, that under etch the structure, and then well, this is silicon substrate, and then we have some dielectric layers and whatever up here, low-cost oxide, so the field oxide, and the general way in which this works is that if you have this field oxide with some holes, you can access the silicon by xenon difluoride etching. So silicon will be etched by this xenon difluoride, this isotropic fluorine gas etch that removes silicon in all directions, and so oxide can be under etched. So you can even think of producing oxide bridges by etching from two sides. Oxide bridges are then covered. Now, once this is done, they're covered by polysilicon, and that's then the polysilicon of the circuit. Yeah, they have some N and some P polysilicon here. It's a double poly process. And, so these structures of N and P polysilicon are then partially sitting on that oxide bridge, insulated by this cavity, thermally insulated from the cavity, of course electrically insulated. Cool. And then such elements can be connected electrically by the aluminum of the CMOS process in series. So when you look at this, you see immediately a thermopile. Yeah? Any of these elements is a thermocouple. So if I have here a temperature T0, and here also T0, and here I have T1 larger than T0, so here is T1, then this contact and this, now maybe I should choose another color, this contact and this contact are hotter than these contacts here. And therefore, if I went there and measured a voltage difference between here and here, a delta V, I would measure a delta V proportional to delta T with what proportionality constant? With the Seebeck coefficient between the N and the P doped polysilicon. This is how thermocouples work, and that's because of the temperature gradient in the material. There's an electric field gradient generated by the temperature gradient with the Seebeck coefficient or thermal power. So let me call this as it is, Seebeck coefficient, OF, or thermal power. In English, they prefer to use the name thermal power, the thermoelectric coefficient. So this electric field generated in the P polysilicon will be in the opposite direction, or I should say, will, if the two polysilicon were the same, the two field directions would be opposite. And so the voltage difference in one direction would be compensated by the voltage difference in the other direction. So we would measure delta V equals 0. But because there is n poly combined with p poly, you have an electric field caused by a gradient, and then an electric field in the same direction the other material by the opposite gradient, because the alpha is opposite, and that adds up to a final delta V that is different from zero if delta T is different from zero. So then you can add a second one and the third one and the millionth one, and you increase that little thermal electric voltage to an appreciable size, and that allows you to measure the temperature difference T1 minus T0, the temperature difference sensor. And the purpose of the sensor actually was to produce thermal flow sensors. So put a sensor on the radiator to measure the thermal flow via the temperature difference the sensor experience in order to record how much heating power is dissipated by this radiator. And if this is done on all the radiators, you know a precious number that you can tell the person who rents the room to say, you spend a lot of energy, you have to pay a lot. My heating, my central heating work a lot. You pay exactly what you use. This is this kind of. Of course, adding up so this is a thermocouple, and when you combine thermocouples, you get thermal piles, and adding up thermocouples into large thermal piles is okay to increase the voltage, but you also increase the resistance of the whole thing. And that means that if you are hooking this up to a circuitry, then you need to take this into account into its circuitries. For instance, wouldn't it be great to harvest energy? There is a thermal flow through the structure, and we have a voltage. Why don't we use that to produce energy? To extract electrical energy. Electrical energy extraction means having a current and a voltage at the same time. That's power. If there is only V and no current flows, there is no power. If there is a lot of current without a voltage, because you short circuit the whole thing, there is no power either. And so harvested. And so you have to design that structure and view of the large facilities of those layers actually that's not a good energy harvesting. You can harvest nano or microwatt. Just enough maybe to drive the circuitry needed to somehow sometimes transmit the information to some central box that wants to hear every hour, what is the heating power being now dissipated. So it's not something, it's no power that you can use to drive something to do. Energy harvesting is a tough topic. Here you have a structure that is also produced by intra-CMOS. So during the definition of all those diffuse structures for the CMOS technology, there is also a definition of a very highly doped P region. In this example, that was invented and promoted by University of Michigan. So Professor Wise, Ken Wise, one of the founding fathers of MEMS technology, the originator, the Khalil Najafi, also famous guy, and worked with this very efficiently. And so this P plus, good. Thank you. I think of it actually in 3 rooms, no, in other rooms, but here I seem to forget all the time. Yeah, okay. So what do we have? We have here this substrate, which is thick, and thick P substrate. And then there is this N epi, and there's this highly doped P plus region, and then the well regions and the CMOS. Yeah, and at the end, actually, so that's not only intra, it's also post. At the end, the whole wafer is etched from the back. The P substrate is etched from the back, and the etching stops at the P++ region. Yeah? That's again an electrochemical effect. Yeah? You need a certain potential difference to cause a chemical reaction to occur. Yeah? And if that potential isn't there, the chemical reaction doesn't work. Yeah? And you certainly know about this redox reactions and the electrochemical potentials, and then you know, it's difficult business. I find. Yeah? The physical chemists know all about it. Yeah? But here the example is that the P++ has its Fermi level at a level that prevents the electrochemical etching at the voltage at which it is. However, the P substrate is removed. And that then means the following, that this is kind of not to scale. You should rather imagine it like this: a thick P substrate, hundreds of micrometers thick, etched right across, and then at the end, there is a thin layer of a few micrometers of P++. And so if this P++ region is defined accordingly, what will it mean? It will mean that you can make some thin silicon structures with some dielectrics and conducting layers on top. And if this structure has the shape of a finger, a needle, then this needle can be really small because it is microstructured. And this is how Ken Wise made the first neural probes. So fingers that can be inserted in neural tissue, in brain tissue, between the nerves, with some recording site, some electrode having contact with the electrochemical environment, able to measure neural action potentials, the variations in potential that come with the action of the neurons. The communication of neurons is potential shifts across their cell walls, and this can be sent outside, and this will be transmitted, will be sent by such a recording site and then amplified on the chip by some in-situ amplifier. So that's one way in which this is used. Another neat way I found is to just do this electrochemical etching right to the end, but then use the P++ as a beautiful geometrical etch stop. So you don't have to worry too much about, is there under etching? Is it stable? Is it a bit more or less? It's the definition of the P++. It says how large a number it's going to be. And so it could be pressure sensors or thermal sensors. Got the thermal sensor seated in the middle, thermal piles penetrating from two sides to have a gap in the thermal sensor chapter later. Yeah, so here are some examples of these needles produced by Ken Wise and his collaborators. They always produced also beautiful images, and then you see that there are several such electrode sites on the needles connected with some interconnection lines to the back, to some circuitry that may be in the back. So let's see some post-CMOS layer micromachining. Again, there's lots of academic groups and companies who do that. I think really, really impressive with this Texas Instruments structure that is now also old by 20 years, but you can buy projectors based on that technology. You can buy photolithography machines based on that technology. And, many subjects. So post-CMOS add-on layer, the Sensirion relative humidity sensor, I mentioned that just by depositing adjustment. By depositing hygroscopic water-sensitive polymer, polar polymer on top, and then packaging the whole thing after the CMOS process has simplest possible scenario. So here are some examples. What you see is again a full CMOS technology here, and then some area with micro machine structures. And what you should see here is silicon germanium. So those materials here are silicon germanium. And silicon germanium can be deposited actually at lower temperature than polysilicon. So you can do it even after completion of the CMOS process. However, note that here some of the materials that are implemented here as metallizations are tungsten. Okay, well, tungsten is known as a metal that can experience high temperatures. It's the one with the highest melting. There's titanium nitride, titanium silicide. Those are also highly stable compounds. So you are not actually restricted so much in this process here with the silicon germanium. And actually, to be honest, the silicon germanium is correct down here. Up here, it could just be a standard polysilicon. Because the CMOS process was perfected in a way to bear the thermal load of the higher temperatures at the post-CMOS process. So that's a special CMOS process, special metallization that can do the job. Special diffusions that somehow are designed so that even after fabrication of the polysilicon, they are at the right depth. And then the silicon germanium, polysilicon germanium, as I said, can be deposited at low temperature, few hundred degrees, 300 degrees, 250 degrees, on top of a planarized, completed silicon based CMOS process with aluminum interconnections. Aluminum, usually after aluminum you don't go above 400 degrees. It's a reaction with silicon and the fusion processes that occur, and so polysilicon germanium is fully compatible with that. And on top of the CMOS wafer can deposit another layer of base metallization, base conductor, another polysilicon germanium layer, a thin one, and then comes an oxide layer, and the second polysilicon germanium, which you can structure, and then a sacrificial removal of that sacrificial layer. Okay, here, this is the Texas Instruments structure, which is a beautiful piece of engineering. So the CMOS process is finished, and below each structure you have a little SRAM cell. This is a kind of a switch that allows to be addressed to apply the voltage that can then be held. And so on top of the CMOS process, there is deposition of a base metallization layer. Then there comes a sacrificial layer of that thickness. So this is here. This is sacrificial. So if we look here, this would correspond to this arrow here, this whitish region. And that in Texas Instruments, the technology is not a silicon oxide. It's a polymer. Photoresist. which is planar thanks to surface tension. And then that is structured to have some holes in it. And then another metallization, series of metallizations are deposited. You see here in black a first layer, which is also a special metallization hinge. Yeah, I say hinge metal. It's a metal combination of Texas Instruments design. Yeah. I would think of titanium nitride or something, but you have to think that this metal undergoes many deformations. The mirror flips, I don't know how many times per second, and that for I don't know how many seconds per year, and that I don't know how many years. So this has to do its job for billions of times, and the metal should not age. Now, when you deform metal periodically, there's always some aging. So the design of the metal to make it aging-proof is a metallurgical task, which they claim to have solved. And the fact that successful products are out there tell me that it works, but they don't tell what metal it is. Okay, so that's a very thin hinge layer, which is under tensile stress to be flat, so that the mirror that is elaborated on this bridge, is not flappy on its support. It's under a tensile stress, but it shouldn't be too tensile either, because if it's too tensile, then you can't rotate the mirror. Again, that is a design challenge, to have the stress of that little torsion bar, or torsion blade designed such that there is stability and there is also mobility at the same time. And actually, the fact that this is slightly, can be stressed and deflected out of plane is actually an important part of the operating of the mirror. I will just say that in a second. And so then there is another metal layer, which is this thicker whitish region here, also here, which corresponds to the blue and the green structures. So this is on the hinge in the middle. That's this this greenish part, and then there is the kind of rigidified support of the bridge, the anchors of the bridge, on either side of the river. To the anchor, and then spans this river. And then what you also see is that actually then there is a next level of elaboration. So another polymer is deposited, which is also structured here. And then the mirror mask, call it aluminum. Texas Instruments knows what. Aluminum reflects nicely. But maybe it's something more complicated, with a little oxide mask to protect this from further oxidation. So maybe it's aluminum. Aluminum oxidizes naturally. It's deposited, and that's then the mirror surface, which, depending on the angle of that structure, will reflect an incoming light beam either onto the point where the illumination should happen, or into some light dump where it is just absorbed, and then produces a black light. So that is how the structure looks like, and the operation is quite interesting. So you see here this base electrode, which can be charged to potential with respect to this electrode. So apply a delta V between these electrodes. One will charge the mirror to a potential, and the other will have this subjacent area at a potential. And the attraction force between here, let me maybe draw this in yellow, between here and here, if I'm correct, causes the tilting of the mirror. Now I have to think, because there is an okay, yes, that's correct. So, and then what happens when the mirror tilts? Imagine this mirror tilting more and more. At some point, these little tips, these tips come to rest on this electrode. Yeah, you see that schematically here. Yeah, and of course they are at the same voltage. So there is no problem of some discharge at this location. Whereas the electrode below the structure that is below here continues to attract the green structure in the middle. And then there is also this protruding post that also attracts the mirror at this level. Yeah. So there is attraction between the blue and the gray. Yeah. Also increasing the torque acting on the mirror. Or mirrors is taking the stronger part of the contribution to heat. Yeah. However, the mirror will stop by contact at these locations. Yeah. So that gives it a well-defined angle of plus and minus 10 degrees. That's important also, that we have the control over the position. Yeah. And now, how do you? There's always this problem of stitching. Now, when two materials touch, how easy it is to get them apart, especially with microstructures. If the torque of the hinge is not strong enough, the mirror will stay stuck in its position. So what happens is that actually one gives the mirror a little voltage pulse via these attraction electrodes, which kind of attracts it rapidly stronger towards the bottom, and then one releases that immediately. So there's a little root bomb, which causes the green part to separate from the gray. And then the mirror is free to be in its rest position, to be tilted either left or right, if you want, whatever the next cycle says. And this is done, I don't know how many times per second, many times per second, because you want to have maybe video resolution, 90 frames per second or something, but what is modern, I have no idea. Let's call it 100 hertz. 10 milliseconds, and those 10 milliseconds must be subdivided into subsegments so that during that 10 milliseconds, the light pulse can be shown either full time, very bright, or half time, half bright, or 10th time. So you have to have this continuum of positive scale, this digital scale of intensity levels that you have to provide. And that means that the shortest time that you are tilting the mirror or not tilting the mirror, tilting in the opposite direction can be very short. Let's say 1,000 levels would be 1,000th of 10 milliseconds, 10 microseconds. So the electronic must be fast. Fortunately, it's CMOS. And say 100 kilohertz. You can do that. So it's a beautiful piece of engineering. Also from the point of micromachining, where interesting problems were fantastically solved, and I found this release method quite fascinating. Yeah. So here are some other pictures. So here you see just this first level of metallization without the mirror being elaborated, and what is the size of this structure? So those mirrors, the size I think is 17 micrometers. That's not so easy to see. So let me draw that here. 17 micrometers by 17 micrometers. It's a small pixel, and you have different resolutions here with you know, VGA and SVGA and you know, probably 4K nowadays, whatever. I don't. Yeah, I haven't looked it up. Yeah. Please look at GND or DLP technology on the internet to know the latest versions. They also have long bars with you know, for different applications. Of course, it can be used for light pattern generations in other scenarios than on a projector. Yeah, here this might be a DND here that produces that image, but you can also project photolithography machines, yeah, in all kinds of different scenarios. So post CMOS micromachining of CMOS layers. Yeah. Well, again, there's lots of groups to do that, and I will just show at the end some interesting approach from Carnegie Mellon, invented by Gary Feder, also a good friend and now a famous person. So what did he invent? He said, okay, if we have a full CMOS process, can we use the CMOS metal layers as masks for etching, you know, into the silicon? Yeah, so this is a more than two metal process. Let's say here with a third metal layer that asks as an etch mask against an etchant that removes the silicon oxide. Yeah, so you can imagine an anisotropic silicon oxide etching process, plasma etching process that removes silicon oxide, of course, everywhere. That is, these oxides on top of the metal, but then here unstopped until one reaches the silicon. And if there is this protection metal here, we will have some fine structure made of oxides, an oxide wall containing potentially other materials like metal 2, metal 1, and polysilicon embedded within it and protected all around by silicon oxide. And then when one of their proposals or one of their realizations, they under-etched the structure by some isotropic etchant. I would propose xenon difluoride. And this beam structure is suspended, yeah, probably hinged or anchored again out of the plane, and this can be combined with various other beams into interdigitated structures again, to be operated as capacitive sensor structures, and an electrode, and there are metals in there to bring in the charges into these electrodes. Although they're racked by dielectrics, they are still electrodes. Not the best possible electrode, but they're electrodes. An alternative is to go with, you can also go with deep reactive ion etching, and then isotropic etching, following that to under etch some of those structures. Also, that is possible. So plasma supported deep reactive ion etching, and so here is a final structure of this one of the sensors. It's I like this picture particularly. Yeah. At some point, I watched some movies by, and now I forgot his name, this Japanese movie maker. Kurosawa. Yeah, you may have heard about him, Kurosawa. Excellent movie. It's castles. Look at that. You can see the samurai walking here. And then the central, you have the central pagoda of the Master Samurai. Well, actually, it's a 2D accelerometer. Yeah, so this is kind of the seismic mass that will deviate the structure in the 2 dimensions. Yeah, and then you see this well connected. Yeah, via these thin beams to other structures that you see here, yeah, with fingers, yeah, protruding between the fingers of an opposite finger system. So these are the interdigitated fingers that I talked about before, interdigitated electrodes that respond to shift in this direction. Shift of this mass in this direction will cause those fingers to overlap more or less, the capacitance to change more or less. So this is longitudinal in this case. It's not lateral like in the other examples that you have seen before. Yeah? These are longitudinal motions. Yeah? And to keep those fingers in place, there are other structures, spring structures, yeah, that make it happen that this structure cannot move in this direction. Yeah, the spring system is suspended on this vertical pillar over the silicon substrate, and it allows only a one-dimensional motion. Yeah? This central mass, however, can move in 2 dimensions. Yeah? And the same structure that you see here, yeah, you see, of course, also opposite, to somehow multiply the signal by 2, but you see also the same structure in the perpendicular direction, which allows to measure the second acceleration as well. And the arrangement of springs, of course, it's good to know that these springs are suspended here, yeah, and here on solid ground, and then there is this connecting bar here, which connects along here to these supports. So there are other bars, and of course, this object can move left and right only, and not in this other plane direction because the beams are so stiff in the longitudinal direction. But they can be bent, yeah, so this horizontal motion in this direction is possible. And then we have more beams attached to that central connection, to our structure here, that now can move only in this direction. Yeah. So half of the motion of this structure, and I should draw the second beam also if I can. Yeah. So half of the motion here occurs at this location and none occurs here. And so this is elastically suspended at these supports and forced into this motion. Now you may ask me, is it also moving in the out of plane direction? Yeah. Yeah, it's quite deformable, so it could move out of plane. But if those beams defining this motion in this allowed direction are higher than wide, yeah, this motion is easy, and this out of plane motion may be hard. Yeah? The stiffness of a beam varies with the third power of the relevant dimension. Yeah? So if the beam is, let's say, 5 times higher than wide, then it will be 125 times stiffer for out of plane deflection than for in plane deflection. So that's good to know also. And as we have seen, such anisotropic structures can be produced by appropriate design and control of the technology. So here is the last slide, for the last minute. So there's some CMOS micromachining technologies we have done it in my own lab. So we have produced some add-on layers. So in a post CMOS way by adding SU8 posts on top of CMOS substrates, and there were sensors integrated below the post so that contact to the post would be same as mechanical stress in the substrate. So this was kind of what we call artificial skin. Touch it and see how it is touched. If there's an array of posts, we have this spatial resolution as we have also with our hands. We are doing a lot of Neural probes where we need special metallizations, yeah, titanium, gold, platinum, yeah, are deposited, iridium oxide are deposited after the CMOS process. We have polymers for waveguides, laser diodes, all kinds of communications. We do tactile sensors also by other ways, by doing reactive ion etching and silicon glass bonding on after CMOS process. This is all post CMOS, post CMOS. Yeah. Actually, everything is post CMOS. Yeah. Then we have done quite a bit of sacrificial aluminum etching for releasing structures, for producing test structures for mechanical measurements. And well, you have seen a nice example of bulk micromachining in this form of the 3D coordinate measurement sensor, but there will be many more, including neural probes. So with that, I'd like to conclude chapter 2, technologies, and next week we will be able to start with magnetic sensors. Something that doesn't actually need so much micromachining. In some cases it is good, but magnetism goes through the materials, so we can exploit it in the structure as they are. But it is still called MEMS because we are doing sensors out of CMOS. Although we did a lot of micromachining here, the next chapter will not rely strongly on micromachining. Okay, with that, I would like to conclude and thank you for your attention and your questions. And, looking forward to next week.